For decades, silicon has been the foundation of modern computing. It works well because it can control electrical signals precisely, allowing transistors to switch on and off reliably. But as chips continue to shrink and demand for performance increases, silicon is becoming harder to scale. Smaller transistors generate more heat, leak more power, and become increasingly difficult to manufacture. Graphene chips are being explored as a possible alternative to traditional silicon-based chips. Graphene is a material made from a single layer of carbon atoms arranged in a hexagonal pattern. It is extremely thin, incredibly strong, and most importantly, it allows electrons to move through it much faster than silicon. This property makes it attractive for use in high-speed electronic devices. The main advantage of graphene is speed. Electrons can travel through graphene with very little resistance, which means signals can move faster across a chip. In theory, this could allow processors to operate at much higher frequencies than current silicon-based chips. Graphene is also highly efficient in terms of heat. It conducts heat very well, which helps reduce overheating. This is important because heat is one of the biggest limiting factors in modern chip design. Better heat management means components can be packed more densely without causing performance issues. Another benefit is energy efficiency. Because electrons move more freely in graphene, less energy is wasted during computation. This could lead to chips that consume less power while delivering higher performance, which is especially useful for data centers and mobile devices. However, graphene also has a major limitation. Unlike silicon, it does not naturally have a bandgap. A bandgap is what allows a material to act as a switch, turning current on and off. This switching behavior is essential for digital computing. Without a clear-off state, it becomes difficult to build reliable transistors. Researchers are working on ways to create or simulate a bandgap in graphene. Some approaches involve modifying the material structure, combining it with other materials, or designing new types of transistor architectures. Progress has been made, but it is still not at the level required for large-scale commercial use. Another challenge is manufacturing. Silicon chip production has been refined over decades with highly optimized processes and supply chains. Graphene manufacturing, on the other hand, is still developing. Producing high-quality graphene at scale with consistent performance remains a technical hurdle. There is also the question of integration. Modern computing systems are built entirely around silicon. Replacing it would require changes across the entire ecosystem, including design tools, fabrication methods, and hardware architectures. This makes adoption slower, even if the material itself shows strong potential. In practical terms, graphene is not expected to fully replace silicon in the near future. Instead, it may first be used in specialized applications where its strengths are most valuable. These could include high-frequency communication devices, advanced sensors, or components that need extremely fast signal transmission. In the long term, graphene represents a different direction for computing materials. It addresses some of the key limitations of silicon, particularly in speed and energy efficiency. But turning that potential into a complete replacement requires solving challenges in switching behavior, manufacturing, and system integration. In simple terms, graphene offers a way to push beyond the limits that silicon is starting to face. It is not a ready replacement yet, but it is one of the most promising materials being studied for the future of computing.